Hello students, in this lecture we are going to study how to calculate electric field due to a dipole. We'll divide this topic into two cases. So first we'll be calculating electric field at a point on dipole axis. So now let us understand what dipole axis is. Suppose if we are having a dipole like this is the positive charge, this is the negative charge, and this distance between both the charges is 2a. Suppose if I draw a line like this, then this can be considered as dipole axis. And now we want to find out electric field at a point which is on the dipole axis. It can be somewhere here also nearby to the positive charge, or it can be somewhere here also nearby to negative charge. We'll be calculating electric field at a point here. So we'll draw the figure for that. Suppose this is our positive charge and this is negative charge. The distance between both the charges is 2a. So if this is the center of dipole, I can say that this distance is a. And in the same way, this distance is also a. So the total distance between both the charges becomes 2a. This is the center of the dipole. And the direction of the dipole is always from negative to positive, and this vector is known as dipole moment. Now we'll draw the dipole axis. So this is our dipole axis. Now we need to calculate electric field at this point P over here due to this dipole. So what we will be doing, we'll be calculating electric field at point P due to positive charge, then due to negative charge, and then we'll be adding both the values of electric field to obtain total electric field. So first we'll draw the directions of electric field at this point due to both the charges. So first, because of the positive charge, the direction of electric field here will be radially outwards. So suppose this is the electric field at point P due to the positive charge, and due to negative charge the electric field will be in this direction, which is radially inwards for the negative charge. You must be wondering why I have drawn this vector longer than this vector. The reason for that is this point P is nearby to positive charge. So if this distance is less, the strength of electric field at this point P because of positive charge will be bigger, and hence I have drawn this vector longer. If you see the distance between point P and the negative charge, then this distance is quite big. So the strength of electric field due to this negative charge at this point P will be smaller, and hence I have drawn a smaller vector. Now the distance of this point P from the center of the dipole is, suppose, small r. So this is the distance of point P from the center of the dipole. Now I'll draw the distance of point P from the positive charge. If you see the figure, what is this distance? It is small r minus small a, this distance. So I'll be writing that distance as r minus a. Now we'll write the distance of this point P from the negative charge. So what is that distance? You can see in the figure it is r plus a. So that distance is r plus a. Okay, so now our figure is over. Now we'll start with our derivation. So the total electric field at this point P will be this much. See, it is electric field due to the positive charge plus electric field due to the negative charge. So now we'll calculate this electric fields separately, and then we'll be adding them. So first, suppose I am calculating electric field due to the negative charge. I'll name it as E minus. We all know this formula. This is the source charge, and this will be the distance of the point from the source charge where we need to calculate electric field. So we'll substitute all the values in this equation and we'll obtain the equation for electric field E minus. So from the figure, if I see, the value of K is 1 upon 4 pi epsilon naught. The source charge, we were calculating electric field due to negative charge, so my source charge will be Q upon R square. R square is the distance of the source charge from the point where we need to calculate electric field. So that distance of the source charge from the point P where we need to calculate electric field is R plus A. So I'll substitute that value whole square. Now here I need to write down the direction of electric field as I am writing vector sign over here. From the figure, just see. The direction of electric field due to negative charge is this, and the direction of dipole is in opposite direction. So I will be writing here a unit vector along the direction of electric field. This is the electric field minus P cap will be the direction of the electric field. So I am writing here minus P cap. This minus is not because of the negative charge. Remember this. Okay, so this was our electric field due to the negative charge. Now we'll write down the value of electric field due to positive charge. Again, from the same equation, okay, what is the distance of the positive charge from the point P? From the figure, the distance between these two is R minus A. So I'll substitute the value over here. It will be R minus A whole square. And I need to write down a unit vector along the direction of electric field. So now just see the figure. This is the direction of electric field due to the positive charge at point P. And what is the direction of the dipole moment? Same. So I can write here plus P cap. So we have these two equations now. We'll substitute these values in this equation. Suppose if this is equation 1, then here we'll write from equation 1, the resultant electric field will be, I'll substitute this value, this minus P cap, I can write that minus sign in between and substitute this value. And the P cap can be taken out common. One more thing can be taken common. You see Q upon 4 pi epsilon naught. So we'll take it out. Okay, so we are left with these terms. Now we'll simplify them. We'll take LCM over here. So this goes here and this goes here. Multiplied by R plus A whole square. P cap remains as it is. Now what is this? You know the formula. This is A plus B whole square. What is A plus B whole square? It is A square plus 2AB plus B square. So by using this formula, we'll substitute the values over here. So what I'll get is instead of r plus a square, I'll be writing r square plus 2ra plus a square minus, this is r minus a square. How it can be written? Just see here, r minus a whole square. This will give me r square minus 2ra plus a square. Now I'll substitute this value over here, but I have a negative sign over here, and I'll open up this bracket. So if I open up, the signs will be changing. So instead of plus r square, here I'll be writing minus r square. Instead of minus 2ra, I'll be writing plus 2ra, and instead of plus a square, I'll be writing here minus a square. Now just see our denominator. You all know this formula also. So instead of this r minus a whole square, I'll be writing r minus a into r minus a, and instead of this r plus a whole square, I'll be writing r plus a into r plus a. So now I'll get r minus a, r minus a, r plus a into r plus a. Now if you see the numerator, all these values will get cancelled. And just see, this is the formula for a square minus b square. This used to give us a minus b into a plus b. So from this formula, r minus a into r plus a, it will give you r square minus a square. Same way, again this into this also will give you r square minus a square. So now we'll be writing in the numerator, add these two terms, so it will give you 4ra, and in the denominator, solution of this is r square minus a square. Again, solution of this is also r square minus a square. So I can write here whole square into p cap. Okay, now we'll take one condition. We'll consider one case for r very big than a. What does this mean? This means that point P is very far away from the center of the dipole. Just see what was r and what was a. This was the distance r and this is the distance a. Now we are considering a case where this r is very big than a. If r becomes big, what happens? This point P goes far away from the center of the dipole. So we'll consider that case. Our point P is very far away from the dipole. Then in this equation, this a can be neglected as this r is very big. So it doesn't make any difference whether we subtract a or not. So on neglecting a, what we'll get? We'll drop out this a, so we'll get r square whole square. Now if you see, in numerator we have r and in denominator we have r raised to 4. So one r will get cancelled and in denominator r cube will be remaining. Now we'll cancel this, so we'll obtain okay. Now this 4 can be written as 2 multiplied by 2. So I have just split this 4 into 2 into 2. What is this? This is dipole moment. It was vector P is equals to 2a into q. So instead of 2a into q, I'll substitute this value. So it will give me 2 multiplied by vector P upon 4 pi epsilon naught r cube into P cap. Now I won't be writing here P cap, as the value of vector P is actually magnitude of vector P into a unit vector along its direction. So I'll drop out this term. I won't be writing it. If you remember, r cap was vector r upon mod of vector r. So it was vector r upon r. Similarly, P cap is equals to vector P upon mod of vector P. And mod of vector P is 2aq. So from this equation, vector P is equals to 2aq into P cap. So this whole 2aq into P cap, instead of this we can write vector P. So this is our required equation. Now if you see in this equation, all these quantities are constant. So I can say that the electric field is inversely proportional to r cube when r is very big than a. And the value of electric field at point P on the dipole axis was this much. So this was your derivation.